Thank you very much. Hello, I graduated from WUZI. Last year I was here, and now I'm working at Advertima. We are a startup based in St. Gallen. We're doing video recommendation based on a person's facial features like age, gender, skeleton, so we can track lots of information like that and then do personalized recommendation. We already raised like 8 million investments. Currently, we are quite a big startup, and part of my talk includes some work that I'm doing, also some paper I read it related to HPC, so I want to share with you. Hopefully, you can get some inspirations. So let's start. And yeah, the topic is basically divided into two parts. The first part is deep learning and HPC. Actually, I regret I didn't participate in the first day session where Dr. Hoffler talked about the parallelization, synchronization of deep learnings. Part of my talk in the first part will be like as-on, more detailed talk in the specific topic he mentioned. And the second part is edge computing, and it's quite a hot topic now. It also relates to not very high-end hardwares, but good hardwares, also with some nice acceleration softwares. It might be, it's very exciting. So what we care, I'm a deep learning specialist, so in our situation, we care speed and accuracy, and in terms of speed, it's different in training. In training, you care about the number of images you process, so you need more GPUs, but there are some problems as we'll talk. And in inference, for example, in my company, our products need to be real-time, so you need to have a higher FPS, frame per second. And in order to achieve that, sometimes you have a budget constraint on the hardware because the customers are not willing to pay more money for the high-end hardware. So you need to do some network compression, model pruning, quantization, knowledge distilling, basically try to get rid of unnecessary neurons or make it compact such that it retains the accuracy but it's much faster. And in accuracy, in training, we care about does it converge well and converge well to good accuracy. And in testing, in inference, since the model is already trained, but we want to make it faster, so we need to keep as much accuracy as we can, but at the same time make it fast. So this is what we care in industry. And the problem with deep learning and HPC is one thing mentioned by Dr. Hoffler yesterday, the batch size. You cannot increase it to infinite amount. For example, we have 10,000 GPUs on a supercomputer, but you cannot use all of them to train because one problem is the model, the training is unstable. It doesn't converge, it diverges at a certain point. And for example, this figure is an experiment from Facebook. They managed to train ImageNet within 1 hour. And what they found is up until certain mini batch size, like 8,000, then the validation error start to increase. So, and they managed to train the model to up until to 8,000 mini batch size using some tricks. So this is not the state out yet. I will talk about more. So what the tricks? First of all, there's some rule called linear scaling rule. Basically, if you have a key GPUs, your batch size should be multiplied by k, and your learning rate should be multiplied by k. If k is super large, and it means your learning rate is quite high, and in practice, because deep learning is quite empirical, it doesn't converge. So it causes a problem, and the strategy first to reconcile that is to use a warm-up. Basically, you are doing initially smaller learning rates, and then you gradually increase that. there are other tricks, factors influencing you do model training when it comes to multiple GPUs. For example, the batch normalization, which is try to bound the weights to a certain threshold where it doesn't explode when you do the gradient update. Momentum, how do you update the loss? The loss should be combined from different, we are talking about data parallelism here, so the data is spent on different GPUs, so you need to combine the prediction, make the loss. Also, how do you do a gradient aggregation? So all these things need to be specially taken care in order to have a trainable system that scales to multiple GPUs. Right now, it's like 256 GPUs. In the future, can be more, but it's not easily you scale 1,000 GPUs, get 1,000 speed up. Sometimes it doesn't train well. So the hardware they're using, of course, is quite state of art. It's not DGX2, but it's still 32 DGX1, NVLink plus the interconnected Mellanox 50 gigabytes Ethernet card. So they don't have the communication latency. I mean, it's covered. So the competition is going on. So there's another paper which try to make it even faster, and we have the it's based on observation. Then traditionally you have the layers of models, and each layer you are giving the same learning rate. Learning rate is quite important hyperparameter in deep learning when you want to train a model. It cannot be too big, it cannot be too small, so it's something empirical. And the question is, what if we use different learning rate for different layers such that you are more tailored for the network, because different layers have different properties. So the scaling factor they found is the L2 norm of the weight over the gradient. And here is the plots where without this so-called layer-wise adaptive scaling, the large batch size doesn't get the same accuracy as lower batch size. Well, with this trick, you can achieve even a little bit better performance. And this is on the ImageNet, where another experiment is done on a ResNet. It's a relatively modern architecture. And as you can see, you can increase the batch size to 32,000, which is 4 times bigger than the previous state of art. With this trick warm-up, LARS, and some learning rate. So you can achieve almost, the same accuracy with the same computation amount of work you need to do. So this is quite amazing. But there's more work with the same author. In this paper, they try to train models with CPUs, basically. And they can do same batch size with same trick. They can achieve training Alex model on ImageNet with about 10,000 CPUs or 2,000 internal Intel KNL systems. The importance of training a model this fast is that as a researcher you can really iterative and to find the optimal model for whatever you are going to make your task better. For example, you can find a better object detector that can be accurate, that doesn't run into people when you put on the automatic driving car. So this is quite amazing. And the framework they are using is Caffe plus MPI or Intel Caffe, where they have support for multi-node training. And we are talking about here is data parallelism. Each GPU have certain data, and they use synchronous stochastic descent because it's more stable than the asynchronous way. So the observation is that with more batch size, you have less iteration if your total amount of computation is fixed. And another benefit kind of is less communication overheads, because each time you update the weights in the parameter server fashion, or in this stochastic asynchronous stochastic gradient descent fashion, you need to synchronize the weights because you have larger weights, and you will communicate less messages, and this can be benefits for training in HPC. Another problem in another task is called object detection. For example, Uber recently had a car accident. It bumped into a pedestrian. It was using object detection algorithm, but the car detected the pedestrian, not that in advance, so it bumped into the person. So in object detection, you need to find where the object is and classify what is it. So traditionally, because we need to deal with super high resolution to find the teeny objects inside the image, so you need to you can only fit 1 or 2 image into 1 GPU. And if you with 8 GPU, you only have 8 or 16 images. And this is not good because it cannot collect enough statistics for the batch normalization. So it also have these problems as mentioned in the classification, failure to converge, inferior results. And last year there is a paper which can scale the detector to 256 batch size, and is winner over this detection challenge by Microsoft, and it trains only in 4 hours instead of days. So one observation of this large batch size is that when you are doing object detection, the green one is the positive objects, the object you want to detect, like the giraffe. And the red one are the negative, the background that you don't like, but you want to mix them, put in the network, and then network distinguish which is which and where is this object. So in training, you want the ratio to be more balanced in order to make the network less biased towards the distribution of the data. So what we found is with larger batch size, the ratio is more balanced than with smaller batch size. And of course, they are using some tricks. For example, they are doing this cross GPU batch normalization. Before we don't do any batch normalization because the batch is small, so we just fix the statistics. And the problem is when you scale to a big batch size, it can fail in training. And with the so-called cross GPU batch normalization, you can scale to 256 batch size. You can achieve within 4 hours and a slightly better mean average precision. So that's all the, from my point of view, the breakthroughs, like in deep learning, where you want to take more resources in HPC, but the problems encountered and problem that it fixed to make it scale to larger system. So another topic is edge computing, because these hardwares become more and more powerful. For example, in our company, we are using Nvidia TX1. It has 256 CUDA cores, more than 1 teraflops per second. It's quite powerful. So the reason it become a hot topic, in my view, is that there's a need for faster inference in real time because of tasks like real-time image recognition, real-time criminal recognition. For example, in China especially, we detect criminals in the metro, in the shopping malls, and also for Face ID, real-time pedestrian detection in automatic driving car. So it should be real-time, while it shouldn't be the hardware shouldn't be too expensive such that it cannot be scaled. So in our company, as I mentioned, we do a multi-person skeleton detection. So all these key points you can detect, and tracking of each person, you got a unique ID for each person, and you do age, gender analysis, eye contact. Are you looking at the screen? So there's some personalized video recommendation for you. So potentially we already have some collaborators with Migros and with other banks. So it can potentially do store analysis, customer or member analysis, something like this. And we managed to put it on the Jetson TX1 because there's budget constraints of the customer. And yeah, let's look at the TX2. As probably you are expert than me, but it's based on TX2. It's based on Pascal architecture. It basically doubles the number of cores and the memory or the storage stuff. So the software then backing up the TX2 is, as mentioned before in the other Nvidia talk, is based on TensorRT. You might have heard about this, but this is basically really beneficial software that comes for free for additional optimization. What it does, once you prepare a data set, you train your model, you can easily port this model into TensorRT, where you got an inference engine, and the engine will do some optimization like a layer fusion, because in deep learning, you have so many layers. Some layer can be combined such that they use less resources. For example, you combine this block into one and vertically, and eventually you combine this block horizontally to be more compact, and it can be more faster. So, but another question is, in the future, there's lots of other hardwares. They are not Nvidia or CUDA related. What about those hardwares? Can we benefit from some from the deep learning models? The answer is there's a new framework called TVM. It's try to close the gap between you have high-level models trained by Caffe or TensorFlow, but you have different hardwares, vendors, AMD, GPUs, you have some embedded devices, and you do not want to hard code to optimize the kernels. So this framework automatically did this for you, and the result is quite amazing. So this is the diagram for that. On the top are the deep learning frameworks. You train some model, and you put this so-called compiler, where it do manage some more better memory management and some other stuff. It basically to optimize the computational graph. And this is not enough. So there's another component called TVM, which can do better kernel, because, for example, in convolution, the same computation can be optimized differently on different hardwares. So it divides some hardware, some primitives to tailor for different hardwares. And here's one simple example, some sample code from the website, where you load a model, then trained from your favorite framework, and then you use this VM to compiler to build the graph. You choose your target, it's CUDA, it's OpenCL or whatever, and then in the deploy phase, you just set the input and you run, and then you get outputs. So you can even deploy to other stuff on, for example, mobile browser. So this is a concrete example where you have 3 deep learning models. They are quite, for example, MobileNet is quite popular on Android, on phones, where because it's much faster than the traditional heavy models, and on a not super high-end GPUs. Let's compare TVM with the ARM compute libraries. So as you can see, it achieves like more than 100% speed up on these different models. So it's quite promising for those people who want to use different hardwares. Also, another example, this is called depth-wise convolution. It's a convolution that are quite popular, for example, in this MobileNet 1, 2, popularized by Google. And the comparison here is done on 2 things. One is TensorFlow 1.2. On this depth-wise convolution kernel, as you can see, the time cost depends on the image input size. You can choose 3 or 4 times speed up. If you further fuse the operator, means you do the computation together, you can achieve even more speed up. So yeah, that's all I want to share with you. The exciting part of deep learning where you can use more GPUs, but there's lots of difficulties. If you have this expertise, you can join this to speed up. And for the edge computing, the small hardware can do more and more because it's has more cores. There's more libraries joining to optimize it for you automatically. So yeah, thanks.